So here's an example of the midpoint rule. So we're going to use the midpoint rule to estimate the area under f of x equal to 9 minus x squared on the interval from 0 to 2 with n equal to 4 subintervals using midpoints. Well, I already said that, so. And I'll point out, using the midpoint rule is more of a method we actually use more when we cannot use the fundamental theorem of calculus and we're just trying to estimate. It's usually kind of less of how we build up the definite integral method. That said, it's still worth talking about. Plus, so the idea here is, once again, we've got the area under some curve. Looks like that. And we're going from 0 to 2. So 1, 2, 3. So we're trying to estimate this area here. So we're going to break that up into 4 equal subsections. So from 0 to 2, my delta x, the width of each subinterval, or the width of each rectangle, is just going to be the entire length divided by n. Which in this case is 1/2. So each subinterval has a width of 1/2. So we go 0 to 1/2, 1/2 to 1, 1 to 1.5, or 3/2, and 3/2 to 2. So I've got 4 separate strips here. And before, if I was going to use, say, left endpoints, then for this first rectangle, the height would be whatever I got when I plugged in 0, which would be 9. And the second rectangle, the height would be what I got when I plugged in 1/2. And the third, 1, and the fourth, 3/2. In fact, let's actually, I'm going to write out the other two just so you can be reminded of what they look like. So if I was trying to find the estimate for the area using left endpoints, which I would typically label as L4, capital L for left, 4 for the number of subintervals, that would be equal to, well, again, it's just a bunch of areas. It's a bunch of bases times heights. Each base is how much? Right, 1/2. That's a lot of B on the screen right there. Nice. Suck it in. All right, good. So anyway, base 1/2. And then if we're using left endpoints, the height's going to be f of 0. And then for the next subinterval from 1/2 to 1, there are not. There are 4. This is just an extra section over here. So if we're looking at what I've shaded in, it's all of this here. It's not this section over here. I count 1, 2, 3, 4 subintervals. So for this first rectangle, if I use the left endpoint, a height of 9. For the second rectangle, base is 1/2. Height would be f of 1/2. Third rectangle, 1/2 times f of 1. Last rectangle, 1/2 times f of 3/2. I don't really want to plug the numbers into the function because they get a little bit gross, but that's what that would look like if we were trying to estimate the area using left endpoints. To go right endpoints, I'm going to make this a little easier. I'm going to factor out the 1/2 since there's a 1/2 factor in each of these. So it'd be 1/2 times. So now for this first subinterval, instead of using the left endpoint of 0, I'm going to use the right endpoint of 1/2. So it's going to be f of 1/2 plus, for the second one, it's a base of 1/2 times a height of f of 1. For the third interval, it's a base of 1/2 times a height of f of 3/2. And lastly, for the fourth subinterval, it's my base 1/2 times the height of f of 2. And then for midpoints, instead of plugging in the left endpoint or the right endpoint, you plug in the midpoint to find the height of the function. So that's actually what I'm going to try and draw here. Probably not super well. Let's grab a red pen, Jay. So if I use midpoints, they're going to be here, 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 and here. And I'm going to use that midpoint to find the height of my rectangle. Same deal here. Same deal here. Same deal here. Notably, at least in this example, these rectangles I've drawn, part of them are under the function and part of them are over the function. That's pretty typical for midpoints, but not always. We actually have to find the midpoints, and there's a couple different ways you can do this. I usually like to find the first midpoint. So between 0 and 1/2, the midpoint's going to be half of a half, which is a fourth. You can also think of it as the average of the two endpoints. The average of 0 and 1/2 is 0 plus 1/2 divided by 2, which is 1/4. So that's going to be 1/4. And then to find the next midpoint, you can either take the average of the next two, which feels like, oh, not really want to do, or you can just add on whatever your delta x is to 1/4. So 1/4 plus 1/2 is 3/4, and that's your next midpoint. And 3/4 plus 1/2, or 2/4, is 5/4, which is your next midpoint. And your last one, if you add on 2/4 again, is going to be 7/4. Right there. So those are the points we're plugging in, and then it's just the same thing. So M4 is going to be, well, all your bases are still 1/2, and now your heights are going to be f of 1/4, f of 3/4, f of 5/4, and f of 7/4. Which we could calculate, just kind of a terrible pain because, right, it's like the numbers are not particularly nice here. So you're plugging in fractions to something being squared, so it gets a little bit dicey, but certainly doable. So typically, when you're estimating the area under a curve, we usually either use left or right or mid, but really where we end up going with this is then taking the limit as the number of subintervals gets larger and larger and larger, so that we can actually calculate the area using the limit definition of the interval. So, questions about this particular example? Doing so much work over here. It's really not my favorite. So, since there aren't any questions, I'm going to give you one to try on your own. So here's what I would like you to do. Express the estimate for the area under f of x equal to x squared plus 1 on the interval from 1 to 9 using, again, n equal to 4 with midpoints. And I find it particularly helpful to draw out the interval to think about where the midpoints are going to land. So go ahead and work on that for a minute or so. Probably been longer than a minute. So similar idea here. I'm taking my entire interval from 1 to 9. I'm finding the width of each subinterval, which is again just your b minus a divided by n. In this case, 9 minus 1 divided by 4 is 2. And for each of these subintervals, we're going to find the midpoint. Now, I made this one a little bit easier to find the midpoint. The midpoint of 1 and 3 is 2. But again, you're just either finding the average, right? The average of 1 and 3, 1 plus 3 divided by 2 is 2. Oh, I know. I was going to label this. This is x0. This is x1. This is x2. This is x3. This is x. Often, if you're looking for a label for the midpoints, it's usually using the bar notation. So like I would say right here that is x1 bar equal to 2. And this is the average of the second subinterval, which is going to be 4. Right. 3 plus 5 divided by 2 is 4. Or you can just add 2 to 2 to get 4. And then here, the midpoint of 5 and 7 is clearly 6. And here, the midpoint of 7 and 9 is clearly 8. So those are my 4 midpoints. And now I'm just going to do the same thing I did before, right? Total area is just base times height plus base times height plus base times. But here, again, if the bases are all the same, you should just factor it out. So it's base times the sum of all the heights. F of 1, sorry, f of what? F of 2 plus f of 4 plus f of 6 plus f of 8. In this case, the function's reasonable enough that we can actually calculate it, I think, without too much trouble. So we get 2 times the f of 2 is going to be 2 squared plus 1. F of 4 is going to be 4 squared plus 1. F of 6 is going to be 6 squared plus 1. And f of 8 is going to be 8 squared plus 1. So we get, I don't know, 65 plus 5 is 70, 107, 127, 107, sure, 124, I think. I'll check that again. 70, 100, 107, yeah, 124. So 2 times 124, which is 248. So that would be our estimate of the area under this curve from 1 to 9. So we're saying that the integral from 1 to 9 of x squared plus 1 dx is approximately 248. We'll come back to that a little later on. So, moving forward, other things to talk about, properties of definite integrals. There are some important properties that we use all the time. Also, I was looking at the lecture recording from class from yesterday, and one thing I should point out, I don't know, and for some reason the audio wasn't working when I was watching it. Okay, so, right, I'm trying to remember, let's see, did I write it down here? I just want to say this one thing real quick here. This integral that he was talking about at the end of class, or somewhere in the middle of class, it's not a huge deal. But technically, this is an improper integral. And what makes it improper, right, is that this function is not defined along the entire interval. So there's actually so the answer he arrived at would still be correct because this one is convergent. But I just point out this is improper, which just means the function's undefined somewhere on the interval of integration, right? Because your function is undefined somewhere on the interval from 0 to 5. So there are methods which we will learn. So later on, when we talk about improper integration, we'll come back to this example and be like, oh yeah, that's how you should really be doing this. Yeah, I wouldn't worry too much about it, but I just see an error. I kind of like to point out like, hey, that's not quite right. So that's something to be aware of for that. And the other type of improper integral, I'll just point out as well, is one where the limit of integration is infinity. So like, for example, this integral from 1 to infinity of e to the negative x is also improper. But we're not quite there yet, so we won't talk about that more. I just wanted you to know that there was a little bit more there that we should have been aware of. Okay, so, sorry, yes.
Is this the only way you can use it in like a summation form?
You could totally do it. So yes, good question. So the midpoint rule generally, point estimate of the integral from a to b of f of x dx. Here's how I would think about it. I'm still going to do the same sort of work. I'm going to draw my interval a to, oh, I should say using n subintervals. So we've got A, we've got B, we're breaking this up into n subintervals. So we call A x sub 0, and then this first right endpoint is x sub 1, x sub 2, x sub 3, x sub 4, all the way till the last one is x sub n, and the second to last one is x sub n minus 1. So then I'm going to find the midpoints. And here's the easiest way to write the midpoints in a summation sort of way. So my first midpoint, x1 bar, is the average of the first two of the left and right endpoint of the first subinterval. So it's going to be x0 plus x1 divided by 2. And x2 bar is going to be the average of x1 and x2. So it's going to be x1 plus x2 divided by 2. And that pattern continues, right? Each midpoint is the average of the right endpoint with the same subscript and the left endpoint with the one lesser subscript. So the x sub 3 bar is going to be x2 plus x3 divided by 2. And x sub I bar, well, the ith one, it should be the average of the one before it, so x sub I minus 1 plus x sub I divided by 2. And those are the midpoints we're going to plug into the function to get the heights of our rectangles. So then we still need delta x. Delta x is your typical b minus a over n. So then our area is approximately, I'm going to write the long way first. It's going to be f of, I'm going to write it kind of the simple way first. Lovely. They're like, let's make it really loud. F of x1 bar plus f of x2 bar plus f of x3 bar all the way to f of the last one, which would be x sub n bar. All of those multiplied by your width of your rectangle, which is delta x. And if you want to write this as a summation, I'm going to write it for you two different ways. You can write it as the sum from I equals 1 to n of f of x sub I bar times delta x. And if you want to be more like kind of driving down into details here, you can write that as the sum from I equals 1 to n of f of x sub I minus 1 plus x sub I divided by 2 times delta x, which you could write as b minus a over n if you wanted to be extra about it. We're estimating, not saying equal to. So to write the midpoint formula, no limits required. But if you wanted to say it's equal to the area, so note the symbol there, right? I'm saying it's approximately equal to this. So it depends on the question being asked. If the question is use left, right, midpoint to estimate the area, no limits required. If instead they say use the limit definition of the integral to calculate the area, where we typically always stick with what kind of endpoints? Right endpoints, although you could use mid or left or anything. That's when you use the limit, when you're actually asked to calculate the area, not estimate the area. And again, I'll point out, we typically don't use this unless we are in the section where we're talking about alternative methods for calculating areas, because there are some functions that cannot be anti-differentiated. So later on, after we've talked about the fundamental theorem of calculus, we'll be like, hey, we can calculate the area from 0 to 2 of 9 minus x squared by doing what's called the fundamental theorem of calculus part 2, where you anti-differentiate each function. You get 9x minus x cubed over 3, and then you plug in your endpoints. So you get 9 times 2 minus 2 to the third, part 2. But I'm just kind of, and we're not quite there. I'm just kind of pointing out that So here's the point though. So that you get something here, you get 18 minus 8/3, which I don't know is what, 48. 18 times 3 is 54, minus 8 is 46, 46/3. Well, hold on one sec. But if you get asked something like this, the integral from 0 to 1 of e to the x squared, you can't use the fundamental theorem of calculus here because e to the x squared doesn't have an antiderivative. So that's kind of integral where then you're like, well, if I still want to estimate the area, then I'm going to use one of these left, right, or midpoint methods to give an estimate of the area. She was first.
If you get the example problem that we just did.
Uh-huh. Uh-huh.
What would you plug in for x of 5 block?
Sure. Well, so in this, you mean the previous example?
Yes.
Let's see here. So the thing is, it gets to be kind of weird. So like here, I would say, well, what would I put? So if I was going to write this as a summation, I would write this as the sum from I equals 1 to 4. My delta x is just 2. And my x sub I, well, let's see, my x sub I bar. So x sub 1 bar is 2, x sub 2 bar is 4, x sub 3 bar is 6, x sub 4 bar is 8. It looks like my x sub I bar is 2 times I. And sometimes it's just kind of by inspection. But really, it's usually going to be some sort of multiple of I plus a little bit sometimes. In this case, plus 0. But it's kind of just, it's not always easy to see what it's going to be. I kind of just looked at this and like, oh, if I is 1, I get 2. If I is 2, I get 4. If I is 3, I get 6. If I is 4, I get 8. My number here happens to always be exactly double I. On the other hand, if I was writing my right endpoints, I would say that x sub I is equal to, this shouldn't be surprising, 2 times I plus 1. Or in other words, my a plus I times my delta x. So really, if you wanted to go the long route here, you could say, well, it's going to be the average of x sub I and x sub I plus 1. X sub I and x sub I minus 1. So the other way you can find this, which I think is more work, would be to say that x sub I bar is my x sub I plus my x sub I minus 1, where I'm just going to replace I with I minus 1. Divided by 2. And if you calculate that, it simplifies down to 2i, right? The plus 1 here, in fact, why not just do it, James? So I get 2i plus 1 plus, distribute the 2 here, 2i minus 2 plus 1, all divided by 2. The 1, and minus 2 cancel. 2i plus 2i is 4i. 4i divided by 2 is 2i, like we said. Oh, sure. So what I said here was that sorry, I'm running out of room here. My x sub I bar, as always, is the average of x sub I minus 1 and x sub I. That's what I've got here. Here's my x sub I minus 1. Here's my x sub I.
Oh.
Right, so my x sub I was 2i plus 1, right? That's how we, and then x sub I minus 1, I'm literally just replacing the I with I minus 1. I would also point out you shouldn't really have to do, like, this is not something someone's going to really ask you. Question?
I was gonna say, so you should find the points like we've been doing and then see a pattern.
So here I'm going to get f of 2i, which then I can plug into my function and say, great, that's going to be the sum from I equals 1 to 4 of, sorry, brain here. Brain is not working. 2 times 2i squared plus 1. And sorry, and apologies, because the other example I did, I thought I was recreating this example, but my limits of integration were clearly not the same, so I didn't end up with anything close to this.
So in In the textbook, when the moment they asked us to do this with the new definition.
Okay, do you see the midpoint? Okay, we can do one. It's kind of terrible, but we can do one. So, look, sure.
Average, the delta x, usually in these scenarios where the limit is, they don't tell us the subinterval is, right? They just tell us.
No, they don't, because typically when you're doing these problems, when you're doing the limit, you're assuming you have n subintervals. So that is always the assumption. And then we're gonna take the limit as the number of subintervals n gets larger. Okay, so sure. Not this one, right? Okay.
In the right corner, right bottom corner, yeah, that one.
Right.
Why is
So it is famously a function that does not have an antiderivative. I don't know why, but it's been proven that it does not. Try to come. I don't want you to waste your time, but I promise you, you cannot find a function whose derivative is equal to e to the x squared. Or actually, you can. Here it is. There's your function, whose derivative is equal to e to the x squared. It's a pain, but that is the only correct answer. But I know, and it's kind of heartbreaking. I don't love it either. But there's actually a lot of functions that do not have an antiderivative. A lot of them are typical function with x squared instead of x. Like sine of x squared, also not antidifferentiable. I know, it's unfortunate. It's sad. You can spend some time trying to think of a function that if you took its derivative, you get e to the x squared. I promise you it will be a waste of time. Nah, waste of time is maybe too harsh. You won't find an answer, but it might not be a waste of time. You might learn something from it. So you asked the question, we will.
Wouldn't that have an antiderivative of sine x?
Not sine of x squared. Not sine squared of x. So this also. Not antiderivative. Yeah, I know. Okay, so we want to try to use the limit definition of the integral. And we're trying to not estimate, but find. Let's not make our example too terrible here. The area under how not terrible do I want to make it? How terrible was it? Was it it's e to the x. Can I see this question? I don't happen to have my textbook with me because I feel like there's a piece of information I'm missing here. Okay, because I feel like I don't want to go on the wrong track here and then say something that's kind of Let's see this here. Let's see. Right. So I would point out it's really important that when you're doing homework problems, you read the instructions carefully, right? This problem actually says use the midpoint rule with the given value of n, in this case 4, to approximate the integral, right? A very different question. Thanks. What's 20 say? Sure, 20 is much more doable. Let's take a look at 20. There you go. It's still not lovely. Was it x squared plus 2x minus 5? Was 1 to 4? Okay, so how do we do a problem like this? Well, using the limit definition. So I'll remind you, when we do something like this, we have to kind of rewrite this as a summation, and we have to identify f of x, delta x, and x sub I. So the function's easy. Our f of x is just x squared plus 2x minus 5. Our delta x is your typical 4 minus 1 over n, which is 3 over n. And your x sub I would probably just memorize the formula. It's always going to be your a plus I times delta x. In this case, it's going to be a, which is 1, plus I times 3 over n. Or as I would probably write, 1 plus 3i over n. And then my f of x of I, kind of terribly, is going to be that thing squared plus 2 times that minus 5. All right. So we're going to do this. Well, let's see here. We're going to rewrite this as the limit as n goes to infinity of the sum from I equals 1 to n of my f of x sub I. So 1 plus 3i over n squared plus 2 times 1 plus 3i over n plus 5, sorry, minus 5. All of that multiplied by our delta x, which is 3 over n. Then we have to multiply the whole thing out. Yeah, it's not too terrible though. So multiplying it all out, we're going to get, let's see, 1 plus 3i over n squared is going to be 1 plus 6i over n plus 9i squared over n squared. Distribute the 2, we get 2 plus 6i over n, subtract 5, all that multiplied by 3 over n. Combine like terms. So let's see, 1 plus 2 minus 5 is negative 2. 6i over n plus 6i over n is 12i over n. And 9i squared over n squared is the only one that has that. Still have to distribute the 3 over n. So we get the limit as n goes to infinity of the sum from I equals 1 to n of negative 6 over n plus 36i over n squared plus 27i squared over n cubed. I stop to check for the thing I always check for when I'm doing a limit definition of an integral, which is that every power of I is 1 less than the power of n that is below it. And I'm good to go here. I've got I to the second divided by n to the third. I've got I to the first divided by n to the second. And I've got I to the 0th divided by n to the first. So all my terms are looking like I expect them to look. Good. Now we break this up into 3 summations, or however many things you have added or subtracted together. In this case, 3. And I really think you can do this in 1 step. I'll do it in 1 and then I'll backtrack and do it in 2. So the final step for breaking this up, I would say, is you're going to have the following. The limit as n goes to infinity of negative 6 over n times the sum from I equals 1 to n of 1 plus 36 over n squared times the sum from I equals 1 to n of I plus 27 over n cubed times the sum from I equals 1 to n of I squared. But the intermediate step that I didn't write down is first just breaking it all up. So you can write it as the limit as n goes to infinity of the sum from I equals 1 to n of negative 6 over n plus the sum from I equals 1 to n of 36i over n squared plus the sum from I equals 1 to n of 27i squared over n cubed. I think you can skip this step, right? You're just breaking it up into individual pieces, and then for each of those pieces, you're factoring out in front of your summation the non-I or constant terms as far as the summation is concerned. And then we have to use the formulas for the sum of I, the sum of 1, the sum of I squared, which I think he expects you to memorize. So we're going to write this as the limit as n goes to infinity of negative 6 over n times the sum from I equals 1 to n of 1 is just n. Then we've got 36 over n squared. The sum from I equals 1 to n of I is n times n plus 1 over 2 plus 27 over n cubed times the sum from I equals 1 to n of I squared is n times n plus 1 times 2n plus 1 over 6. Okay. I don't want any of you to multiply these out. Or I should be, I want for none of you to multiply these out. You shouldn't do more work here than you need to. So let's think about what we're going to get. Negative 6 over n times n is just negative 6. I'm not writing the limit anymore either because I'm going to be taking the limit in this step. So if, we're not going to, but if you were to multiply out this fraction here, the leading term of the denominator would be 2n squared. The leading term of the numerator would be 36 times n squared. And the 36 divided by 2 is what the limit would be. So we're going to get plus 36 divided by 2. Similar idea here. I always like to look at the denominator first because it's easier. The leading term of the denominator would be 6n cubed. The leading term of the numerator would be 27 times n times n times 2n. So it would be 27 times 2 times n cubed. The work I'm not doing, but what I will show, but again, I really, really can't stress how much you should not write what I'm about to write, or at least in practice, is we've really got the following. The limit as n goes to infinity of -6 plus, if I actually multiply this out, it's 36n squared plus 36n all over 2. If I actually multiply this next part, it's 54n cubed plus 81n squared plus 27n all over 6n cubed. And I'm just looking at the quotients. Sorry, I forgot an n squared on the bottom here. The quotients of the leading coefficients. But you shouldn't have to multiply it out to see what those quotients are going to be. You do have to be careful about that 2 there. It gets missed often. Don't forget about that 2 there. It's important. So then we end up getting -6 plus 18 plus, let's make this easier, plus 9. So we get 27 minus 6 is 21. And one second. If you really wanted to check your work and you knew the fundamental theorem of calculus part 2, you could be like, okay, well, let's check real quick. The integral from, I forgot what it was, 1 to 4. That seems like, I don't know about this. I don't know. Let's check my work because I don't know. This feels not right. It feels suspiciously like it could be not right. So I'm just going to say the thing that we haven't technically learned yet. Fundamental theorem of calculus part 2 just says you can find the net area under a curve above the x-axis by finding the antiderivative of your integrand. In this case, x cubed over 3 plus x squared minus 5x. We don't need a plus c when it's a definite integral. And then evaluate that from 1 to 4. Always the upper value first minus the second value. So I'll point out also, the upper value doesn't actually have to be bigger. We usually prefer it to be, but it can be written in any order. It's totally fine. It just means a different thing. So here we're going to get 4 cubed over 3 plus 4 squared minus 5 times 4 minus 1 cubed over 3 plus 1 squared minus 5 times 1. And if we simplify this, 64 minus 1 is 63, and 63 divided by 3 is 21. And then 16 minus 20 is -4, and minus 5 is +5. Oh, but I forgot the 1 there, minus a 1, and so we have exactly 21. Oh, good, it worked out. You had a question? Or
Yeah,
comment?
my question was basically just why couldn't we do that with the start, the question probably specified.
Right, so if the question says use the limit definition of the integral, you could do this and get no credit. Is kind of what's going to happen. Like so there's an exam question that said use the limit definition of the integral. It's fine to do this to check your work, although, sorry, I think that's it. Although I actually wouldn't recommend checking your work, because if you've done all this work and you get a number, you'll still get some partial credit, even if your actual number is not the right number. Whereas if you check this work and it's not right, you're going to drive yourself crazy and waste time trying to fix it when you don't have a lot of time to spend. And I feel like I saw a hand over here. Yeah. Say that one more time. Oh. So there's two different things, and yeah, fine. So we'll talk about it. So let's go ahead and talk about the fundamental theorem of calculus parts 1 and 2. Even though there's some properties of integrals we should get to at some point. So fundamental theorem of calculus, which often gets abbreviated as FTC, parts 1 and 2. So part 1 is actually the more important part. But part 2 is the part we actually use more of the time. So here's what part 1 says. Here's what part 1 says in words. The derivative and the antiderivative undo each other. Like we've seen a lot. So in fact, let's write that out in words. The derivative and antiderivative undo each other. That is the whole gist of the fundamental theorem of calculus part 1. Here's how we write it. We say that the derivative of the integral from a constant to x of f of t dt is equal to f of x. Don't worry, we'll do some examples on this in a minute here. But that's what the fundamental theorem says. If you take the derivative of the antiderivative of your function, you get back your function. Right, that's part 1. Part 2, which is also referred to as the evaluation theorem, tells us how to find the area under a curve. So that's about, so tells / informs how to find, I really should say the net, or I think you called it in class the algebraic area, the net area under the curve that's above the x-axis. Or in other words, area that's above the x-axis is counted as positive, area that's under the x-axis is counted as negative. So here's the actual way of writing it. It says that the integral from a to b of f of x dx is equal to, I usually write it this way, capital F of x evaluated from a to b. Other people prefer to write it as capital F of b minus capital F of a. Where, I'm going to say words, but I'm going to write something different. Where capital F is an antiderivative of little f. But the way we write that is the derivative of capital F is equal to little f. That means the same thing as the words I just said. The words I just said is capital F of x is an antiderivative of little f of x. Which is something I've done twice today already, right? I've found the area, the net area under a curve above the x-axis by finding the antiderivative of the function that we're finding the area under, and then substituting or plugging in the endpoints of my limits of integration. Top one first, bottom one second. So let's look at some examples about how the fundamental theorem of calculus part 1, because I do think it's important and something people get hung up on quite a bit. Right. Net area under the curve. Sorry, I forgot an important one. Under f of x. Sorry about that. So let's go ahead. Some inspiration here. Sorry. Okay. Cool. What's that? Oh, sure. Sorry. Sorry. People are looking over there. Apology, it looks terrible. So here is a very kind of typical question. Let's start off with something easier. I want to find the derivative of the integral from 3 to x of 4t cubed dt. Most of these questions, the point of them is that you shouldn't be doing a bunch of work. You should be getting to the answer real quick. Here's the short way to do this. So answer A, 4x cubed. End of story. The derivative of the integral is the function you had inside, except you have a change of variable. Instead of t's, which is kind of referred to as a dummy variable, you're going to have x's. Here's what's really going on. So here's the longer way of answering a question like this. I'm going to actually do this integral using the second part of the fundamental theorem of calculus. So I say, okay, great. The derivative of the integral from 3 to x of 4t cubed dt. I'm going to anti-differentiate 4t cubed. I'm going to get t to the fourth. Technically t to the fourth plus c, but we don't really need the plus c because if you had a plus c, it would cancel out. Think about it this way. Yeah, think about it this way up here. If I have the integral from a to b of 4x cubed dx, and I got, say, x to the fourth plus c evaluated from a to b, look what happens when I plug in b. I get b to the fourth plus c. When I plug in a, I get a to the fourth plus c. And what's going to happen to those c's? They're going to cancel out. So we don't need to write them. You totally could if you really wanted to, but no one ever does. So here, we're going to get the derivative of the antiderivative t to the fourth evaluated from 3 to x. Top limit first, bottom limit second. So that's going to be the derivative of x to the fourth minus 3 to the fourth. What's the derivative of x to the fourth? What's the derivative of 3 to the fourth? Right. So look what we've done. We took an antiderivative, we replaced t with x, replaced another t with a constant, and once this, right, this is a once this is a constant, its derivative is going to be 0, so it doesn't matter. And then we took the antiderivative, then we took the derivative, and we got back to where we started, except now we have an x variable instead of a t variable. That's pretty much the whole, that's not the entire story, but it's most of the story with the first part of the fundamental theorem of calculus. Is that if you do an antiderivative and then replace t's with x's and then do a derivative, you're going to get back to where you started with x's instead of t's. But then we like to ask questions that are more, well, where we can't actually use this process of actually showing all the work. So for example, you might get asked something like, find the derivative of the integral from -2 to x of t e to the 4t. And while, yes, eventually we'll learn how to integrate something like this, that's not the point of the question. The point of the question is to apply the theorem and be like, okay, well, I know if I anti-differentiate and then differentiate, I'm going to get back to where I started. So I can swiftly say here that my answer is going to be x e to the 4x. Sometimes we try to write a little bit differently. Like for example, if I said my function was y equal to the integral from 1 to x of sine of t divided by t, I should be able to ask you all to find dy dx. It's a different notation to ask the same question. Find it. Find dy dx. You should be able to write it down in like 10 seconds. It's been more than 10 seconds. Here's the answer. Dy dx is sine of x divided by x. This function, I believe, also is famously not antidifferentiable. Yeah.
For y equal, should it be by dt instead of dx?
So one more time.
For y equal, should it be dt instead of?
Thank you very much. Yes, that is a common error that people make all the time. I could maybe pretend that x that looks close enough to a t, but you're totally right. It should be a dt, and I definitely did write dx. Yeah, I will say the Dell will probably also make that mistake at some point because it's such an easy mistake to make. Yeah, so I would try not to make that mistake, but please do call me out on it because it's easy to make. So it does get more complicated. I know. Let's look at something like I want to find the derivative of the antiderivative from -4 to x x cubed of cosine of t dt. So here, the answer isn't just going to be cosine of x or cosine of x cubed. There's more to it. So again, I would say let's explore this one in a longer way. Let's actually do the work. Because again, cosine is a function we know how to anti-differentiate. Okay. What's the antiderivative of cosine? Sine, positive sine. Whereas the antiderivative of sine is negative cosine. And what's nice about sine and cosine is their antiderivatives have the opposite SIGN sign from their derivatives. Right? The derivative of sine is cosine, the antiderivative of cosine is negative cosine. The derivative of cosine is negative sine, the antiderivative of cosine is positive sine. So that's one way I remember it. So here, that's going to be the derivative of the antiderivative of cosine of t is sine of t evaluated from -4 to x cubed. So then we're going to find the derivative here. Well, sorry, we're going to plug in first, apologies. So we plug in x cubed first, we get sine of x cubed. We plug in -4, we get sine of -4. And now, using the chain rule, what's the derivative of sine of x cubed? Right, cosine of my stuff multiplied by the derivative of my stuff. What's the derivative of sine of -4? 0. I don't know what sine of -4 is, but I know it's a constant. I know it's never changing, so its rate of change, its derivative is 0. So our final answer here is cosine of x cubed times 3x squared. The general way we answer a question like this, or I should say the more general version of the first part of the fundamental theorem of calculus is that the derivative of the integral from a constant to a function of x, not just x, but a function of x, of some f of t dt. The way you want to think about it is you're essentially plugging g of x in for t, but then you're multiplying by the derivative of g of x. Just like we did here, right? We plugged in x cubed where t was, and then we multiply by the derivative of x cubed. And again, it's really because you're taking this, okay, so here's what's really happening. What's really happening is, okay, if we were going to do this the long way, even though I don't really love it, but we're going to, you probably don't need to write this down, but you certainly can. I should say, you don't need to write anything, right? You don't have to write anything down. I'm a person who learns by writing things down. You might be a person who learns better by hearing them or seeing them, which is why we try to do all the things. But this, not so important. So, sorry, the next input, right? So if we were to anti-differentiate this, here's what we would get. Well, I'm going to use standard notation here. The antiderivative of little f is capital F. So we're saying we're going to get capital F of t evaluated from a to g of x. With the reminder that the derivative of capital F is equal to little f. Right, that's what it means for capital F to be an antiderivative, is that its derivative is equal to little f. Okay, great, I'm going to plug in. So I'm going to get the derivative of capital F of g of x minus capital F of a. Oh, look, it's a composition of functions. I'm going to use the usual chain rule for taking its derivative. I'm going to do the derivative of the outer function, leave the inner function alone, multiply by the derivative of the inner function, minus the derivative of f of a constant. Well, f of a constant is a constant, and its derivative is going to be 0. And then, hey, look over here. F prime is really just f. So I can rewrite this as f of g of x times g prime of x. Look at that. So that's what's going on there. Right? You're anti-differentiating, but then you're plugging in something more complicated than x. So we differentiate it, you have to use the chain rule to differentiate it, not just the regular derivative rule. But then we can answer all sorts of questions like, in fact, you all can answer something like, I'll do it first. Something like, for example, we want to find the derivative of the integral from 0 to the natural log of x of sure, e to the t plus cosine of t dt. Oops, sorry, terrible. And again, while you could actually do this one the longer way, we don't want to. We just want to use our thing. So we're going to say, well, we plug in our limit that's variable. So we're going to get e to the natural log of x plus cosine of natural log of x. All of that multiplied by the derivative of the natural log of x. And I would feel ashamed of myself if I didn't simplify this, so I have to simplify it, because e to the natural log of x is just x. But normally, there's not a lot of simplifying that you should do here. If you really want to get crazy, you can write this as 1 plus cosine of natural log of x all divided by this, if you really want to simplify it all. But really, this is what we should be focused on. The rest of this is just me not being able to let it go. Yes. Right. We're not typically doing the work in between when we're finding the derivative of an integral. You want to avoid doing that work because it's not really what the question's asking you to do. Let me have you all try one here. See what else we got here. Oh yeah, sure. We'll go there in a second. Let's say we want to find the derivative of the integral from 2 to x to the 6th of sine of t squared dt. Do it. Give me 30 seconds. And this one you couldn't do the long way if you wanted to, because sine of t squared cannot be antidifferentiated. But we don't need to be able to do it the long way because that's not what we're being asked to do. So I'm going to plug in x to the 6th for t. So I'm going to get sine of x to the 6th squared times the derivative of x to the 6th, which is 6x to the 5th, which I would simplify as sine of x to the 12th times 6x to the 5th. I'd probably even write the 6x to the 5th first, but I didn't, so oh well. What happens? And this actually kind of goes back. Oops, sorry. The slope on this thing is just a little too steep, I feel like. Oh well. Not your problem. I mean, it is kind of your problem. It's more my problem. So what if instead I had asked about the derivative of the integral from x to the 6th to 2 of sine of t squared? What does that mean for us? Well, it's a good question. So here's what that, and so we're going to take a minute to talk about why we're going to get what we're going to get. So let's leave ourselves, we'll leave ourselves some space for the answer. The answer is going to be very brief. So, geez, I'm just looking at that. It's like, it's so tilted. It's just jarring. Sorry about that. Maybe let me fix my camera here just so I can. Okay. Okay, cool. So what if instead of doing the integral from a to b of f of x and getting the usual sort of limit definition, what if we switched a and b, where we're still imagining, right, that a is less than b, right? We're still thinking about finding the area under this curve here. Well, if we switch a and b, something happens. So actually, I should have written one more step here. Apologies. That's an N. A fair question. I will point out that I should have written one more thing here. Limit as n goes to infinity of the sum from I equals 1 to n of f of x of I times b minus a over n. Right? Our delta x is b minus a over n. Now here's what changes. Each of your x sub i's is still essentially the same. You just maybe going from right to left instead of left to right, but you're still using the right endpoints to find the heights of the rectangles. But if I write this out in the same sort of way, since A is on top and B is on the bottom, my delta X is technically calculated as A minus B over N. And well, maybe not unfortunately, but it is true that A minus B over N is going to be negative. Right? A minus B is a negative number because A is less than B. So we can rewrite this as the limit as N goes to infinity of the sum from I equals 1 to N of f of X of I times -1 times B minus A over N. And now this looks exactly the same as that, except it's multiplied by -1. So this is totally equal to -1 times limit as N goes to infinity of the sum from I equals 1 to N of f of X of I times B minus A over N. But that is just the original integral. Or, long story, much shorter, when you interchange the order of the limits of integration, it changes the sign of your integral. Or to say it in kind of a weird way, if you integrate from right to left, you change the sign of your area, which feels kind of weird, but it's what happens. So here, what that means for us is since our limits of integration are in the opposite order we expected them to get, we could in fact just rewrite it as the negative of the derivative of the integral from 2 to x to the 6th of sine of t squared dt. Although I feel like you can even skip that step and just say, yeah, we know it's going to be the opposite sign we would expect to get. So here we're going to get negative sine of x to the 6th squared times the derivative of x to the 6th, which is 6. Or in other words, the negative of the answer we got for the previous one. So when you have a variable thing in your lower limit, it means you're going to get a negative. So let's look at a couple more examples. We're almost, I wouldn't say done, but we're almost through this section of things. If I wanted to find, say, the derivative of the integral from, sine of x to 5 of t cubed times cosine of t dt, I would put the minus. So here's what I'm going to do. I'm going to pretend like the sine of x is on the top.
How do you know that A is greater than B? With the limit. So how do I know that sine x is greater than 5?
We don't. Because it's never actually greater than 5. But so let me back it up here. We'll come back to this example in a second. Let's say we had an example where we can actually kind of do it the long way. Let's say we have the derivative of the integral from, I don't know, x cubed to 4 of, let's make it easy, James. Let's go secant squared of t dt. Time for the long way. What's the antiderivative of secant squared? Tangent. So it's going to be the derivative of tangent of t evaluated from x cubed to 4. Okay. What do I plug in first? 4 or the x cubed? The 4. Always the top minus always the bottom. Oh, minus the bottom. So we get here the derivative of tangent of 4 minus tangent of x cubed. So then taking the derivative of that, the derivative of tangent of 4 is 0. The derivative of tangent of x cubed is secant squared of x cubed times the derivative of the inside. And there's where your minus sign is coming from, because it's the lower limit, not the upper limit. And it doesn't really matter what the respective value is, but the other thing was to show kind of that's why we get the minus sign, because there's this difference here. So up here, not doing any of this work, we would say, okay, great, it's going to be negative because sign's in the bottom, or my variable's in the bottom, lower limit, and then we're just plugging it in. So I'm going to get sine of x quantity cubed times cosine of sine of x multiplied by the derivative of sine, which is cosine of x. Kind of terrible. right? I'm just plugging in sine for every instance of t, and at the end of the process, multiplying the whole thing by the derivative of sine of x. So here's your antiderivative. That's not this. Here's your f, your actual function, not your antiderivative of sine of x times here's your derivative of sine of x. And then finally, the most general version of this is where you have variables in the top and the bottom limits. So for example, we could have something like here. Always paper. Where do you go? Example I was looking for. Sure, we'd have something like, let's say we have, sure, r of x equal to the integral from x to the fourth to e to the x of cosine of t squared divided by t dt. And I want to find the derivative. So essentially the idea is do the top thing first, do the bottom thing second. Or I should say, do the top thing first, subtract, and do the bottom thing second. So we're going to get here, so first I'm going to plug in e to the x for every t. So I'm going to get cosine of e to the x squared divided by e to the x, multiplied by the derivative of e to the x, which is e to the x, minus, same idea, but now we're going to use x to the fourth instead of e to the x. So we're going to get cosine of x to the fourth squared divided by x to the fourth multiplied by the derivative of x to the fourth, which is 4x cubed. And let's not simplify that, even though I want to. So, sure. So it's coming from the second part of fundamental theorem of calculus, where when we evaluate a definite integral, we get the antiderivative with the top limit plugged in minus, that's where it's coming from, the antiderivative of the bottom limit plugged in. What's the derivative of f of 5? It would be 0. What's the derivative of cosine of 5? It's 0. Because cosine of 5, even though it's terrible, is just a number that never changes. It's a constant, right? If you don't see a variable like x in the expression you're differentiating, it's a constant, even if it looks funky. Even if it's like e to the fifth power. Is there a variable in there? Nope. So the derivative of e to the fifth is 0, not 5e to the fourth. Or not e to the fifth, right? Sorry, mixing up my wrong rules there. So the most general version of this whole thing is that the derivative of the integral from h of x to g of x of f of t dt is equal to f of g of x times g prime of x minus f of h of x times h prime of x. But one more to grow. Oh wow, time really flies. What time does this class end? In 4 minutes? Okay, we won't do another example because I should talk about the G's, but just kind of got carried away. Sorry about that. Sometimes you start talking about something interesting, and you're like, okay, well, so let's talk about the second part of the fundamental theorem of calculus for a moment here. And here's how we kind of can get there from the first part. So there is this whole like proof of the fundamental theorem of calculus part 2, which is interesting, but not really what we need. So let's look at the FTC part 2. So here's what we have. We know from the FTC part 1 that the derivative of the integral from some constant to x of f of t dt is equal to just the function you have inside there, but with x instead of t. what this means for us, right? So how do you undo a derivative? With an antiderivative. So we can say then, if you just have the integral from a to x of f of t dt, it's equal to any antiderivative of f of x, which I'm going to write using the usual notation, capital F of x. And I am going to throw in a plus c here. Yes, I know this is definite technically, but I kind of do need to, I'm trying to work out exactly what it is. So then, two things. If x is equal to a, well, let's rewrite this. I have the integral from a to a of f of t dt, and I have it equal to f of a plus c. But how much area is under f of t if I start at a and I end at a? 0. So that's equal to 0, which tells me that the constant here, c, is equal to negative f of a. Cool. Because, so the reason there's a c there is because we're saying here, if the derivative of this function is equal to f of x, then the function is some antiderivative of x, but it doesn't have to be, it could be f of x plus 2 or plus 7, because we're trying to be very general here. And really, we're trying to use this to our advantage to see what the other theorem says. So now, what if we let x equal b? Well, then, just plugging in b for every x, we get the integral from a to b of f of t dt equal to capital F of b plus c. But c is that right there. So we actually get that it's equal to capital F of b minus capital F of a, which is exactly what the second part of the fundamental theorem of calculus says. Kind of tricky, right? It is a little tricky. So, for example, I know it's 11:49, so I'll do one quick example. If I wanted to find the definite integral from 2 to 5 of 2x plus 3, all I would do is anti-differentiate this integrand. I would get x squared plus 3x evaluated from 2 to 5, and then I would get 5 squared plus 3 times 5. That's my capital F of 5 minus my 2 squared plus 3 times 2. That's my capital F of 2. My antiderivative evaluated at whatever point I'm plugging in. And then we can simplify this. It's going to be 25 plus 15 minus 4 plus 6, which ends up being 30. So all of this kind of machinery to get to the kind of more useful piece of information that if you're trying to find the area under a curve and that function is antidifferentiable, so it's not sine of x squared or e to the x squared, then we can find the net area under the curve above the x-axis by anti-differentiating the function, plugging in the right limit or the top limit first, subtracting and plugging in the bottom or the left limit second. And I would say more, but it's 11:50.